Hi, my name is Sarah Cornwell, and in this segment of our presentation, I'm going to talk a bit about language data, both text and speech data, and about how the nature of language data and the thickness and richness of language data allows algorithms to reproduce biases. Uh, so, um, Language data can be thought of as containing multiple layers. You can build language up from the smallest segments of individual sounds or letters up to meaning-containing segments like words, and then larger and larger up to entire works. Works are affected by what medium they're presented in, and they're affected by the larger social context of both the communicator and the intended audience. And these layers are interrelated with one another, meaning that if we have relatively small pieces of information from one layer or another, we can make inferences. We can sometimes make inferences with some accuracy, probabilistic inferences, that is, about the other layers. So if you know that someone uses a phrase like shopping trolley, you could infer, probably correctly, that they are in the British English social context. So what kinds of information can we find in text, written text? Well, the list on the left is some of the things that people try to identify about authors using text, using machine learning right now, with varying levels of success. And this task is called author profiling. Um, while with text data, this is going to be not always accurate, and of course, it is probabilistic. We might immediately realize that there can be issues with trying to extract these ethical issues with trying to extract this data from text. So what kind of issues are there specifically with machine learning? Well, as I said before, the layers interact with one another, but also different features of a text or language segment tend to cluster together. So if you intend to train for one element like age or gender, you may inadvertently train for elements which are strongly correlated with that element. This is a type of bias that can be reproduced in machine learning. As well, different features are politicized or stigmatized differently by different populations. So what a linguist may understand as dialectical difference might be considered simply bad English or an error by someone else, and the way that the machine learning algorithm will treat that information depends on how it is trained. So for example, if you train a spelling correcting algorithm only on English, on American English, of course, it will recognize British English as wrong. And this is especially concerning when we think about the fact that many dialects are stigmatized, even though there is nothing wrong with them. So for example, Black English or African American Vernacular English has special grammatical functions that aren't present in other dialects. One example is called habitual be, where the verb be is used to communicate that a behavior is a habit or regularly done. So the difference between she is running and she be running is that she be running implies that she runs regularly or that running is a habit for her. However, people who aren't familiar with Black English won't necessarily recognize this as an information containing segment and might instead consider it an error. So if we don't accurately, if we don't ensure that our training data represents the diversity and the complexity of the real world context of language varieties, then our machine learning algorithms are going to reproduce the same biases that we have about language when we train them. So this is especially a concern with unsupervised training, because unsupervised training allows the algorithms to choose which features are important, which features correlate with one another, and it weights the features on its own in a black box, meaning that we don't know which features it is using, and we don't know how it is weighting those features or That is, how strongly it's considering certain features over one another. So if you want to train without supervision, you need to ensure that your training data is diverse enough so that, or that biases are controlled for in your training data. Um, Otherwise, the social patterns of language that exist are going to be reproduced by your algorithm, even if you don't want them to be. So for example, if you are trying to train an author profiling task to recognize men's writing versus women's writing, it may instead learn about men's topics and women's topics and sort people accordingly. But in reality, we can all talk about all topics, so this would be a bad cue and would create a highly biased result. And these sorts of concerns are even more severe when we think about spoken language, because speech contains not just the word itself and the letters, but the individual pronunciation of those letters. And by that, I mean the sound itself, the sound quality, can be measured in a lot of different ways. For example, pitch, timbre, and sonorance. You may have heard of vocal fry or creaky voice, and tone changes or prosody. And all of these things communicate demographic data. They communicate our age, our gender, and our dialect, which can also include features which code for our race, our class, as it were, or at least our class aspirations, and our religious affiliation in some cases. It also gives information about what other languages we speak, how fluent we are, and it lets us know if the speech was done by reading or spontaneously, and it can also encode health information. So this company, as an example, Sond Health, claims that they make 4,000 different measurements on a 6-second voice clip, and they also claim that these 6-second voice clips can be used to monitor a variety of health conditions, some of which are listed on the left. And this is obviously a problem uh, because if we don't know or understand that our voice can communicate these things, then we won't know to teach our algorithms that they exist. So we may inadvertently train our algorithms to be biased against people because of these factors when they correlate with one another. If factors correlate with one another, the machine learning algorithms will relate them to one another, but we don't always want those correlations to be reproduced in the final result, so we have to control them. Spoken data is identifiable, meaning it can be used to identify individual humans, just like a fingerprint. Your voice is unique to you. As an example, the Australian Tax Office uses 120 measurements from a single sentence, and they consider that adequate to identify you just as much as your birthday or name might. So in conclusion, users are often unaware of the quantity and qualities that they communicate when they speak or write. And also programmers can't be aware of all the possible types of things that users might be communicating when they speak or write, and how every one of these factors might interrelate with one another, and therefore have inferences drawn by the algorithms. Our best practices must be to try to examine biases, predict where biases might exist, and then train our machine learning algorithms to realize that even though these features occur together, they should actually be treated independently. As well, we need to ensure that we use quality data that adequately represents the full diversity of human speech if we want our algorithms to also represent the full diversity of human speech. Thank you.